So this is station 7. This is a thermal energy apparatus. On the right here, I have hot water that just came off the hot plate. On the left, I have cold water that just came out of the refrigerator. Both of them are 150 milliliters. So I'm going to pour the cold water in and put the lid on so that we can get a temperature. And I'm going to put the hot water in. And I'm going to put the lid on so I can get the temperature for that. And I'm going to slide them close together. In the back, you see this bar, this aluminum bar. That is the heat conduction apparatus. What's going to happen is that bar is going to be in those holes, this hole here and this hole here, and it's going to allow heat from the hot side to transfer over into the cold side. So right now, we're looking at about 6 degrees, 5 degrees on the cold side, and 63 or 64 degrees on the hot side. So that's the starting temperature, 6 and 63 or 64. So we'll put the metal bar in, and this starts the 4 minutes. Also, initially, just to show you, the starting temperature of the bar is 74.6. So if the cold is flowing up through the bar, then that bar will go colder than 74.6. If it's the heat, the thermal energy that's flowing through the bar, then the bar will be warmer than 74.6. All right, so we are at 4 minutes. On the left, the cold water is now at 8 degrees Celsius, so it went up. And the warm water is at 58 degrees, so it went down. And more importantly, let's take a look at our... Our bar is running at 83 now, so the bar is warmer now than it was at the start. So, see, there it is at 84 now. The bar is warmer than it was at the start. So that's station 7. All right, in 3, 2, 1, pull! This motherless class wins!
How does a hockey puck slide so fast? Sports officials have timed the speed of a hockey puck at over 110 miles an hour. But what makes it skedaddle at such high speeds? Is it the frigid surface? Let's go inside the ice. These molecules are bound tightly together, but a tight molecular structure wouldn't make the surface very slippery. A loose, fluid molecular structure would. What's that sitting on the surface of the ice? It's a very thin layer of water. And take a look at water's molecular structure. Because it's a liquid, its molecules slide around freely, making for a much more slippery surface. See how easily the puck glides on that thin layer of water? The weight and friction of the puck itself causes the surface layer of solid to turn to liquid, creating a thin lubricant between the puck and the ice.
So I don't have a hockey puck, but I do have ping pong balls, and they have very low friction because they're circular in shape. In order to answer the two questions at the bottom, there's a question about two objects moving with equal speed towards each other from the opposite direction. So I'm going to send these two ping pong balls towards each other. They're going to collide, and something's going to happen. All right? I'll do that again. All right? So you can see that as they collide, they start to move in the opposite direction. So they transfer energy to each other, and they begin moving in the opposite direction. Now, if one of them was motionless when the other was sent in, then something different is going to happen. They both move in that direction. I'll repeat. All right?
Example 2. Food. All of the foods you eat contain chemical potential energy in the bonds of their molecules. When you digest your food, these bonds are broken. Just like the fuels, when the bonds are broken, the chemical potential energy is released. Remember, chemical potential energy is contained in chemical bonds. It is released when chemical reactions take place. Thanks for watching!
All right, Freedom 8th graders. So this is my son's Connects Space Mountain. We're going to use this to talk about potential and kinetic energy as you review for FCAT. So as we bring the car up, it's building potential energy as it goes up the mountain. Here at the top, it has the most potential energy when it's at the very top, but has not yet gone over the top. That's the top of the tallest hill. Every time it goes over a hill, it loses a little bit more energy. Not that it loses energy, but that the energy is being converted into sound, thermal energy with the track, and motion energy as the car pushes molecules of air out of the way. But it converts that into motion energy. And as it travels down, right there, at this point, when it's going its fastest, but it is at the lowest point of the track, it has the most kinetic energy or motion energy and the least amount of gravitational potential energy. So what winds up happening is the chain on the roller coaster has to lift the car back up to the top of the hill. Otherwise, the car will not have enough energy to continue on.
But we love you, Walter Lewin. We love MIT. So we must love the United States. I mean, that's an incredible statement. As long as I'm healthy, physically and mentally, I will teach